Good afternoon, everybody. Welcome to CppCon again. It's amazing. Woo! Feels good to be home. I'm Titus Winters. I'm from Google, and I'm going to talk today about those things. If you listen to colleagues of mine like Chandler Carruth, people that work in compiler optimization and think about why C++ succeeds as a performance-oriented language, you're going to hear phrases like higher level abstractions, coupled with the normal C++ slogan of we have zero cost abstractions. And the idea here is when we have more expressive tools to express our intent, and the compiler can see that we haven't pierced through those abstractions so that it can do the escape analysis proofs, then it's able to more effectively reason and optimize. And you see this with things like string and vector. When you have a higher level thing, the compiler can prove, oh, you haven't actually modified any of this. I can see that your pointer to your allocation is stable. I don't have to refetch all of this stuff. I can just optimize, right? Like the higher level abstraction gives you the ability for the compiler to do a better job. And further, when you have those higher level abstractions, and we use them consistently, then that also gives you sort of choke points and centralization that you can use in theory in response to changing conditions. So for instance, if the ratio of, say, memory to CPU costs in your environment changes dramatically, then you could imagine if you have enough control over your standard library or your vector and your string and your utility code types, you could change the constant that is used when you're resizing as you grow. Right? So for instance, if you find that CPU costs are dominating and your hits to the allocator, copies and moves, and aggregate CPU costs are particularly bad, but you have so much RAM to spare, then you could tweak things so that you grew 3x. Right? You're going to copy and move things less frequently. Right? You're going to waste more memory on average. Right? But if your trade-offs are, if you know how to do the math between CPU and RAM costs, then maybe that makes sense. Or if you find the opposite, you're spending too much on RAM, you might grow only 1.5x. Right? This is still not going to change your algorithmic growth patterns, right? But it does give you a different ratios and ability to trade off and optimize. The abstraction helps the optimizer. The consistency is valuable for all of the users, and the centralization helps the maintainers of those abstractions balance aggregate resource costs. If you listen to colleagues of mine like Hyrum Wright or Matt Koulakundis on the totally opposite end of the spectrum here, you hear stories about our attempts to, again, optimize and improve interfaces, but we're doing that through refactoring the code itself. And a lot of our long-term work in libraries at Google requires us to have the ability to change code, sometimes centrally, sometimes diffusely across the code base. This is, again, an exercise in finding the important abstractions and either changing their implementation so that all users get the boost at once, or upgrading users to better abstractions as we identify them. So in the centralization case, we see this in most traditional thinking on refactoring and optimization. I remember being told as a student that 80% of your cycles are spent in 10% of your code. There's a hot path or a busy loop somewhere that's doing the bulk of the work. That's not actually particularly true today, or at least not in our experience. The profiles tend to be a lot flatter than that. There's no one thing that is super hot, at least in our production workloads. But there are still, of course, places that use up a lot of juice. The allocator, mutexes, the networking stacks, those sorts of things. And when you can find those central improvements, then that's a very good thing. But we're also saying that we can optimize broadly, find a pattern that is not right, and fix that pattern in many, many instances across the code base. And so you could see this in changing from standard hashes to abseiled hashes. Big performance boost, use string view more consistently, find patterns where we're making redundant copies of strings or missing calls that stood move, and we can get sort of nebulous, ambient performance gains. Right? But in both of these cases, either the centralized or the distributed approach, we're again requiring consistency. Right? We can optimize the allocator, and we do, but that is hampered when the old implementation gave out tuning parameters and controls. We could build tools to remove copies and pass more efficient parameters, but if your team built a string type for yourself that we've never seen before, then our pattern matchers aren't going to kick in and we're not going to be able to perform this sort of ambient optimization for you, right? And yet, we see that a lot of discussions over the past couple years, or at least the ones that weren't COVID related, seemed to all converge upon this theme from so many different directions that the extra extension points, the non-standard ways of doing things, the places where we cracked it open and didn't use the default, these configuration knobs, especially the ones that purport to be about performance, are actually antithetical to those use cases. Especially when we have the wrong knobs, the wrong abstractions, then that gets in the way of both the centralized or distributed optimization work. And critically, we need to realize that configuration, especially performance and optimization configuration, is an abstraction itself. It can be well designed or not. And just like any other form of abstraction, we lose the ability to reason about our changes to decide if they are an improvement or if they are safe when we don't know how an interface is being used. Remarkably, I think a lot of the time, this sort of configuration exists specifically to pierce the abstractions. Let's look at some sort of abstract examples. If you've got a system that works on exactly 3 types, it works on int and double and string, you have a certain amount of reasoning available to you, right? Any particular change that you're making, you can walk through all of the use cases for that. If I have a I/O streaming gadget that has an internal buffer of 64K, I have a certain amount of understanding of like how that's going to interact with read calls and whatever. But when you extend things to work on arbitrary types or user configurable buffer sizes, it's harder to prove that any change is safe, much less an improvement. And yet, none of us is surprised to see requests from users to enable these sorts of changes. This buffer is too big on my platform. Can I get a knob so that I can specify it directly? I've got my own string type. Can I use that instead? From a user satisfaction or a product quality point of view, though saying yes to those requests feels right. It's one user-provided buffer size. What's the worst that could happen? But we increasingly find that these matters need to be handled with great care, especially the interfaces that you're designing that are going to be around for a long time. Like, what is the right size for an intermediate buffer in a streaming I/O interface? Right? Raise your hand if you're going to participate in this example. Everyone just raise your hand. Great, okay, good. Keep your hand up, or how many of you think it would be okay for the buffer that is backing my network socket to be 256K? Keep your hands up. How many think 512K? How many think a meg? Okay, so we're kind of losing faith at about a meg. All right, that's interesting, right? So great, so we'll call it a megabyte. Is that the right answer if this code is going to run on the 486 that I grew up with? Probably not, right? Like, I was always thrilled when my 486 wasn't doing anything in the VGA buffer because I knew that there was like 64K of memory I could use right there. Like, allocating a megabyte, like, that's beyond me, right? And similarly, if this same buffer is going to be used in 2050, I suspect that we might want to reevaluate as well, right? So, of course, we're going to need some ability to tweak it. But what I'd like to argue, among other things, in the course of the talk is giving the user the ability to directly specify that buffer size might not be the right answer. There are sometimes better ways to express these, and there are higher level abstractions. Everything interesting in software is a matter of these trade-offs, and the trade-off at play here is this. For systems that will live a while, for interfaces, for code that is going to last and be used by more than a few people, how do we want to configure them so that they're usable in new environments and will span the test of time without hampering our ability to make future changes and optimizations, right? This is the tension. This is the hard part. And in this talk, I want to specifically focus on 3 main forms of customization and extensibility. There's configuration, settings, tuning parameters, optimization knobs. These are things like setting timeouts and buffer sizes. There's features and experimentation. I work for a web-focused company. We've written a bit about the use of runtime configuration for safe rollouts and experimentation and feature releases. And as it turns out, there is some overlap between these ideas and the practices in how we do refactoring or migration, where we're trying to change default behaviors. So we'll talk about those. And then there's extensibility, which I'll touch on a little bit at the end. This is the idea of letting users provide their own callbacks, algorithms, data structures. But before we get into that, it's certainly worth pointing out a little bit of context. Right? I've been working on C++ library infrastructure at Google for more than 10 years now. And in fact, I wrote up a brief summary of my philosophy to design on some of these questions about 5 years ago. And I'm not going to say that my approach here is the right answer. It's design. Some of this is a matter of taste. Some of these things will eventually emerge as truths. I hope that I've hit on a couple of those, but we'll see. But some is definitely context dependent or just fashion. One of the things I really like about there being a design track at CppCon is so that we have a place to bring these ideas so that we can hopefully get consensus and build up a better foundation and framework. So for what it's worth, a little bit of my design philosophy in my own words. I say, people often seem surprised at my priorities. Arguments of, hey, we could build a thing, do not interest me at all. We have so many things already. Adding a feature that is used rarely is often worse than not building that feature at all, especially for low-level interfaces, and for several reasons. The first, if 99% of your users understand an API through the lens of the default settings, then the 1% of users that change that setting are at risk, right? APIs that are built on top of it, systems that are built on top of it, have a pretty good chance of just assuming that default behavior and sort of ignoring your funny edge case, right? Leaving your 1% semi-supported. And I regard this as probably worse than unsupported because it's going to fail late in development and in surprising ways. To bring this back to being a C++ talk, hey, this is what happened to vector bool. Hyrum's law applies, always. Mostly this has to be mentioned here because the more surface you expose, the more you are constrained by Hyrum's law problems. And of course, compile time detection is good. This is a statically typed language, hooray. The compiler and the type system are good places to have your invariance. Correctness proven at compile time is preferable to discovering the same things at runtime. And really, this is just good application of the whole shift left terminology. It's cheaper and more reliable to detect problems statically at compile time, so we'll do that if we can. This also, I think, applies to configuration, or configuring maybe based on target platform instead of dynamically at runtime, right? The more that you can make those things statically knowable to the compiler, the better the optimizer is going to be able to do, and the fewer questions that your maintainers are going to have to ask, right? The earlier that you can specify things, the better. These ideas have been pretty resilient over the years, so we'll start to, let's get into configuration for reals. And for the purposes of this talk, mostly I'm going to talk about this as specifying inputs and parameters that tweak the general operation of the component, mostly in a sort of optimization and performance sort of setting. So there's settings and knobs and timeouts. And we configure things all the time. It's around us everywhere. And I think a lot of good design should be informed by the world around us, even when we are talking about interface design. Your faucet has one major mode, right? It has on and off, which is probably a gradient. That's fine. But it has a very important configuration, hot and cold. As anyone that has used a faucet can tell you, that configuration is imperfect. Just because you turn the faucet on to full hot does not mean that you necessarily get hot water. You're configuring the steady state or the ideal state. Or maybe you're just telling the faucet system which of its inputs to prioritize. Any of these views on that are correct. You hope that you are specifying an output, but the specification is kind of inexact and aspirational. And yet, I don't see us rallying to redesign faucets. It's a little messy. Sure, is up hot or is down hot? That is a fair point, and that one does get me. But I would say your thermostat is also an instance of interesting design to look at, right? It is also off and on, or off and heat and cool, but it has a slightly different mode in its configuration, right? You pick the temperature you want, and it does whatever it can to make that happen, right? You are specifying directly the output. And side note, pet peeve, just set the temperature to what you want. If it's too hot in here, setting it to 50 does not make it 75 any faster, right? You're just making it noisy and it's a whole thing, but anyway. So that's maybe interesting, faucets and thermostats. These are two designs for things that I think we're basically okay with that have sort of different logic systems behind them, right? One is setting a target directly and running a bunch of software to figure out how to hit that target. How much do we need to run the heater, the cooling, or the AC system, whatever, right? And one is sort of configuring the back-end mixer and hoping that the inputs to the system are roughly what we expect, right? But both are, if I may, very focused on outcomes. Are the other tools and utilities and technologies in our lives the same? How's about the microwave? For most of us, certainly any of us that went through being poor college students, you go through a period of reading the directions and then you sort of get a sense of how long do I need to nuke this thing for, right? And your major configuration here is how long am I cooking this, right? That's it. Easy peasy, right? But not exactly foolproof, not entirely satisfying, but like you could follow the recipe, I guess. If you're going really fancy, there's also adjustment to the power settings, real gourmet mastery for microwaves. But I bring the microwave up because if we're feeling extra lazy or extra lucky, there are these pre-programmed special function settings like popcorn. And that seems very in line with the thermostat example, right? We're picking the outcome that we want and we're leaving the mechanism to the programming. But here we see a difference. Here we see a problem. Most purveyors on popcorn specifically say on the bag, don't use the popcorn setting. In fact, when I was searching for Creative Commons images of popcorn, this was the first image, and it says it right there. If you dig into this, it's because the popcorn setting is not magic. It's, we bought a bunch of microwave popcorn and took the average of how long you should cook it for. That's it, right? No magic, no smarts, right? It's just the lowest common denominator cooking for microwave popcorn. It's not paying any specific attention to the details of your popcorn. Some newer models try to get super fancy by adding a humidity sensor to the microwave on the notion that popping corn releases a lot of moisture, so when the humidity level goes up and then starts dropping again, I guess your popcorn is done. But, you know, the Orville Redenbacher website gives us a very good explanation for how to properly cook microwave popcorn, which is you listen for it to stop, right? And we don't have that hardware on any microwave, right? So on the one hand, the popcorn button, picking an outcome, is a very nice, tempting idea. But it sort of falls short in the implementation because the implementation doesn't measure up. And that leads to a very interesting quandary. Should I do it directly because I know better than the system I'm interacting with, or should I use the button knowing that it expresses my intent even if the results are currently underwhelming? Maybe there could be a software update for my microwave. In this case, I know for sure that my microwave is not going to get a software update. It is not going to gain the magical ability to properly pop popcorn, and so I do it directly, and I curse the cruelties of the world that make this button so misleading. But interestingly, I think that part of the question here is there someone that I actually trust that is going to help close the gap between the intent that I expressed and the outcome that I got? And I would argue pretty clearly that there is not in the case of microwave popcorn. Commodity microwave ovens just don't have the hardware or software to get that right. And so I know from the start that it's never going to get any better, and so I can stay away from it. Hopefully the things that you are configuring in your software are not like that. But I'm pretty sure that good quality software and good quality interfaces that you are configuring are tied up in either everything is perfect and matches your outcomes exactly the way that you want, and it will stay that way forever for those very few things that don't need to change over time, or things are malleable enough for us to give you better results in the future if you trust us to change things. So from looking at things in my kitchen, basically, my current reading on configuration is we like to control outcomes, right? The thermostat is great design, We will settle for controlling inputs when there's a clear path from what we are controlling as the input to the outcome that we can get to, right? We, as humans, can understand the faucet or manually programming our microwave. Mechanisms that purport to control outcomes but that don't do a great job of matching those intents will be an attractive nuisance like the popcorn button. But this is a computers and C++ conference, so maybe we should talk about those things. What sorts of configuration do we see commonly in C++ and in our tech jobs? Let's start with something C++ related, the compiler. Compilers have dozens, probably hundreds of command line flags, but in my experience, we talk about two classes of flags more than anything else. What are we optimizing for, and what classes of warnings are we going to diagnose on? You might already see where this is going. With optimization settings, we tend to express those in broad strokes, sort of desired outcome fashion. Turn on aggressive optimizations, or optimize for binary size, or build this as fast as you can. We don't get down into the fiddly parts, right? The flags are -03, not -0 unroll loop count equals 5. We say broadly -w all much more than we list all of the individual warnings for wall. And we chuckle nervously at the fact that on most compilers, wall is not actually all the warnings, it's just the good ones. But we can, in some cases, break open those abstractions and toggle the more fiddly bits, but we tend not to, and we probably shouldn't in general. I think we generally have kind of a funny taste when you see the build configuration have tons and tons of subtle things that you can't entirely understand at a glance. O1 is like, or the -O is like your thermostat, right? You aren't specifying how long it should run. You aren't specifying how many BTUs to pump into the system. You aren't specifying how much CPU to burn on doing this optimization. You're telling it what your goal is and letting it do the best job possible of achieving those intents. And even if -W all is misnamed, you're still broadly saying, hey, please keep me on the straight and narrow. Don't let me do anything too weird. Interesting. Let's look at some more examples, maybe of places where we don't like the design. Our configuration is not satisfying. And rather than throwing shade at others, let's use a slightly sanitized example. This is configuring a buffered reading interface that we use internally to read certain forms of sequentially structured data. I maintained this interface for a bunch of years. I never made a whole lot of changes to it, I just kept it working. But here's the current configuration for this reader. There's the memory budget. This is the budget for the internal data buffer. There's seek back, which should maybe be seek back bytes, but since we're reading sequentially structured data and potentially have very big files, if we're doing sort of a batch processing, then we might say, split this into 100 megabyte chunks, and the seek back is how much we're willing to jump backwards if we didn't start on a sequence boundary, so that we don't miss the sequence that spans that 100 megabyte gap. There's enable async IO, which is a Boolean, and it says, are we trying to make asynchronous read calls either by spinning up another thread or relying on non-blocking file operations for the underlying file types? If that is specified, then we have buffer size, and in the case that enable async IO is specified, then this is the actual memory budget for that internal data buffer. And the delta between memory budget and this is the memory size allowed for other in-flight async operations. Otherwise, this is ignored. The look-ahead budget is how much to prefetch if we're doing asynchronous I/O, which implied is supposed to be less than buffer size. And prefetch on open doesn't actually have anything to do with asynchronous. It's just, do we prefill the buffer starting at construction? It happens to only be triggered if you have enable async I/O turned on. Totally clear and straightforward, right? Great configuration. I posit that many of you probably have a gadget somewhere that you're working with that's similarly terrible, so don't judge me too hard. But to be fair, this example was actually drawn from an interface that we have done textbook studies on as interfaces that evolved without really any oversight. For a few years, any proposal that added tests and didn't break the build was basically accepted. And now we know what happens when, oh, we could build this, is taken as a proxy for, oh, we should build this. Anyway, if we compare this configuration to the lessons that I think we've tentatively learned from previous examples, there's a lot more math and control logic, right? Subtraction on byte counts, Boolean comparisons, distinct modes for enable asynchronous I/O, and yet the semantics of the whole thing are basically the same, right? All of this is just to try to make your whole use of this widget more efficient in some sense. But it's pretty fiddly, and it's hard to connect any configuration that you see with this to how do I configure these things to get the optimization or the results that I want. By comparison, I don't think any of this configuration is actually tied to the results that you want. Instead, if we were looking at configuration based on intent, I think we could do a lot better. Like, have one enum. What are we optimizing for? CPU usage, number of I/O operations, or total memory? Right? I suspect that you could introduce this and do a pretty solid job of like obeying that intent and doing a better job of optimizing based on, oh, this user happens to know that this is going to be a CPU constrained environment, or this user happens to know that we're latency sensitive, right? And you could probably do a better job with this level of, this is what I care about, instead of this is how you allocate that buffer size. So there's also, if we wanted to be fully, like match all of the semantics that were available in the other thing, I think we could add maybe these 3 additional pieces. And I really like specifying it as max memory size. I'm not saying I'm gonna go allocate a buffer this big. I'm saying, please tell me, what would too much be, right? And I don't promise to use all of that, because I might actually know that that is too large a buffer for this use case, right? But like, it's okay for you to tell me what's too much, right? I kind of like this idea. So anyway, with these options, say all 4 of them, who would prefer the existing set, right? With the enable async I/O and the Booleans and all of that. Anyone want to raise your hand? No shame. I mean, I'm polling. It's very scientific, right? Okay. Who would prefer this configuration? Oh, there's a whole lot more hands. Who would prefer this proposed configuration if I told you that a very good engineer who would handle the details of making optimize for actually do the right thing so that it's not just the popcorn button? That should be every hand, right? That's what I thought. I find this interesting. So now we'll make it a Titus talk. Hey, how do these approaches work when our technology needs to change? Our context is evolving in some fashion. Let's imagine that the maintainer of this library identifies new optimization opportunities. There's hardware accelerators for compression. We could change the CPU usage by relying on that. Or there's, like I said before, a new understanding of the trade-off between CPU and RAM usage, right? What parts of these configuration styles work and which parts don't? With this sort of outcomes-focused configuration, the burden is on the maintainer to honor that broad request, right? You're not promising any particular outcome, but you are saying, I will do what I can to minimize the number of I/O operations. I will do what I can to make sure that I'm not copying a bunch of data wastefully for you, right? Your default sizes per mode there could presumably change over time as you learn more about the system and your production environments and you learn to re-optimize. Right? All that's really required of the interface is the semantics of, I'm going to read all of these records out of this file. Right? And so everything else is just choices in the optimization space. I think it's pretty likely that few users of this style interface are going to find ways to depend on it in weird Hyrum's law cases, right? Because you haven't given them a whole lot of hooks to really hold your hand or to force your hand. And with fewer interfaces exposed and more orthogonality, you have more protection, basically, right? And as a result, if RAM prices spike, you could, for a modest amount of effort, change your allocation sizes to match and see a benefit from all users. One of the things that I also like about this approach is you don't even have to actually have a different mode for those 3 modes to start with, right? You could have, hey, tell me what you're prioritizing for. I'm not going to do anything different whatsoever, right? You're still matching the semantics of the contract, but when you learn that there are users that are like, oh, memory super matters, then you can drill down into those special use cases and refactor the internals to match those needs better, right? Because they've already expressed, I'm in the class of users that need to worry about memory, right? I think that is kind of a cool approach. With the more fiddly configuration, all of that is a lot less clear, right? We're clearly leaking the implementation details. Like just seeing the configuration options for memory budget, seek back, and enable asynchronous I/O, you can probably start sketching in your head exactly how all of this works, right? Because the abstraction has leaked heavily. And that leakiness also means that we're giving users more opportunities to screw things up. So we'll take memory budget, for example. Out of 13,000 uses of this interface, I found 100 that were setting that value at all, right? Which, remember what I said about red flags and like, hey, this is concerning, right? I suspect that this is not actually the right sort of configuration and people are going to misuse this. One of those sets it to 256 bytes, which seems kind of heinous to me because like you're going to pay I/O costs and doing reads at less than a kilobyte granularity. Like what? Really? 256 bytes? Okay, that's wild. And one of them sets the buffer size to 256 megabytes and spins up one such reader for each of n files. And I think that there's often about 1,000 of those files. This also seems a little excessive to me, right? The rest in between this are kind of hard to interpret. I have no idea if they're better or worse than those outliers, right? Now, imagine that you are the maintainer of this library acting on information about new hardware, new optimization opportunities, new resource costs. You've given users this detailed control over the buffer. Time to ask yourself some important questions. How many of them set that based on actual knowledge or research into how it's going to work in practice and what they're optimizing for? And even if they did that research to set that value well, at some point, that's the past, right? How long does that research stand for? Is it still the correct answer? How many of them are going to howl because you changed something that they've hyper-tuned? And if you change that thing that they have hyper-tuned, do they get the veto over the other 13,000 users that are just accepting the defaults? Right? I don't know how to answer this question. I think probably not, but you're going to have some people upset one way or the other. Having only provided these fiddly knobs, you can't tell what their intent was. Did they set it to 256 megabytes because they know that the files that they're reading are always less than that, and they're optimizing for I/O operations? Or did they set it to 256 meg because it runs during the startup of a process that has very large buffers, and so they know that buffer size is always available, and they're reducing CPU costs to get into steady state sooner, right? Is there any way to tell? In a perfect world, there would be some comment explaining the rationale for this setting, but that's not going to happen in practice. Unlike other things in refactoring and optimization, changing our software, we know how to change a lot of things safely because tests. But these sorts of configuration changes don't usually result in semantic differences, mostly just timing and resource consumption. And as far as I know, nobody has a really robust model for testing that. Certainly, I don't see it. Any test that you might have that's trying to do that is probably going to be flaky and is not going to really well match the normal sort of pass-fail semantics that we want from our unit tests. So under the model that change must be possible in our software, these sort of granular performance tuning options are kind of a real stumbling block. And worse, they become a haunted graveyard, right? Every time someone resorts to leaning on these options, some fraction of them are wrong from the start. But importantly, they're haunted graveyard because when you come across set the memory budget to 256 megabytes with no comment, it's really hard to evaluate, like I said, whether that choice continues to be right. And so I pretty much guarantee that anyone spotting that code is just going to leave it alone. Like, I spotted the 256 megabyte times 1,000 example in code like a couple weeks ago. I did not go fix that, right? Yeah, thanks, Matt. Partly it's because change is scary, and partly because there are so many possible options, right? And partly just the reasoning, the intent is completely opaque. So it's now in SRE terms a haunted graveyard. It's a part of your system where everyone is afraid to touch it because no one really knows what's going on in there, right? You're just going to leave it alone and back away slowly. Similarly, it's more than just buffer sizes, right? We have systems internally like pipeline processing things with configuration like how many threads should I use? So imagine that we default that configuration to 16 threads in the first version of this pipeline, and then some users find that their workloads are unusual and they get better throughput when they change that down to 8. So they hard code it to 8 in their usage. And then all of the rest of the optimization groups go to work. We change our context switching latencies, we improve I/O operations, change the default number of threads to take advantage of those optimization changes. But anyone that hard-coded it to 8 misses most of that benefit, right? And increasingly has increasingly wrong values for those things because the context around them has changed. Right? It may well be the case that after 1 or 2 rounds of optimization to the pipeline, that they would be much better served with 32 threads or just stick with the default. Most of the time, just stick with the default, right? But it's really, really hard to prove any of this. And so they stick around and pessimize things. We see this so much. Does this mean that all granular configuration knobs are bad? I don't think so, right? Having control over singular specific details is sometimes necessary, right? You set a timeout or you provide a port number, right? These are still just integers, right? I'm not saying all integer configuration is bad. Right? Usernames, database paths. These all seem like the right level of abstraction as far as I can tell, but those all have a semantic meaning, right? From the outside of the thing that you're working with, and that is different in my mind from the memory budget example. So we get this slide. Configuration should be orthogonal, should be focused on outcomes and intents, and that's really the big one. It needs to be minimal, and it should be easy to reason about, right? If someone that is unfamiliar with exactly the system is going to look at whatever you've done to configure it and run away screaming, then you probably have the wrong sort of configuration interface, right? If they can look at it and say, oh, I see roughly what you're doing, like, I trust that that's basically sensible, then you're probably on a better path, right? Interestingly and satisfyingly, since I started poking at this idea, I've seen a few others that have basically independently come up with a pretty similar list. It's the sort of thing that's never going to be easy to prove. It's design guidance after all, but it does seem pretty broadly applicable. Another place where we see this sort of configuration and options is during refactoring and migration. I've given similar examples in the past, but it bears repeating. We use these sorts of configurations and tweaks during migrations to express the intent of, I want the default behavior before we change the default behavior. This is a textbook mechanism for doing that sort of migration. I gave this example in my 2019 design talk. There is a question. I will wait for the question. Go ahead.
Okay, question from online.
Yes.
What does number of threads look like in semantic configuration?
I don't think that there's a semantic configuration for number of threads, really. Like, I think it's at most, you might specify maximum number of threads or, hey, how much parallelism is available in my hardware? But like, that one is very optimization. Like, yeah, it's basically an optimization. Great. We went through that example last year. Another example, same basic idea, right? This works for all sorts of things. One of the earliest large-scale changes we ever did at Google was done in exactly this way. We wanted to change the default visibility for our build rules. And so step one is to make the current behavior, every library in our code base was publicly visible, so everything could depend on everything else if you didn't make cycles in there. And that wasn't exactly what everyone signed up for, because some things are like, this is internal to my team, I don't really want everyone else using it. So we went through and codified the existing default behavior by stamping, hey, the visibility is now legacy public in every file. And then as soon as every file had that, you could change the default, if you don't have such a stanza, to be private. Now every new file is private, or someone has picked specifically what they want their defaults to be. You didn't change any of the behavior in the system, right? When you're in the middle of a migration, this is a very useful technique. But I think it's also interesting to note that it is still about intent. In both of these examples, we're making the code change to make explicit the original behavior and thus the original intent of the user. I'm going to skip talking about legacy naming. And that sort of brings us back to this slide, right? At one point, I was trying to add extra bullets to this slide as we went through the talk, and then I kept finding like, nope, every time I come up with a new example, it's just, hey, it kind of needs to be focused on outcomes and intents. And that's not implementation details, right? I'm not leaking the internals of my system. It is a little bit leaky in the sense of it shows what the default used to be, but that's not really the same. It doesn't hurt the optimizer, it doesn't harm the maintainers. Other places that we see runtime configuration happening, since I work for a web-focused company, we can talk about production. This is another incredibly important domain for configuration, experimentation and release rollout. Both the SRE book and the Flamingo book talk about feature flags for configuration. This is in many respects part and parcel with general DevOps policies and trunk-based development. Don't rely on dev branches, commit to trunk. If your feature isn't ready for prime time yet, don't call it. But you still include the tests for it. Your feature is included in the binary for development builds, so you can see, you can poke at it yourself, you runtime enable it. It might be stripped out in release builds, all of those things. When it's time to see whether the feature really works in the wild or is providing value at all, then you use an experiment framework or a release algorithm to turn on the feature for some subset of usage, either as an A/B test or a gradual rollout. If it turns out to be bad or buggy, then at runtime you can turn that feature off again without any real penalty. This requires that that functionality is gated by this configuration, and that setting of that is managed by either your release engineers or your experiment frameworks or your rollout systems. And this is all very valuable. And again, it works best for high-level features, right? Not the fiddly details, not the implementation, but the statement of, do you support this feature in this mode, right? It is, again, just about intents. So the only thing I can really add to this list is clean up after yourself when you're done with, this style of development. Otherwise, you just have tons of dead code paths and code bloat and bit rot happening. But it's not a whole lot of depth to that statement. It's just, yep, we configure based on intent. That's the important part. I will breeze through real quick what happens when we step up the configuration by a level of abstraction. Instead of you handing me values to configure my behavior, you hand me functions or types or the like. You probably first experienced this with one of two things, either callbacks or polymorphism. And there's certainly a few design lessons to be had there, although they're, I think, a less deep insight than what we saw with configuration. With callbacks, most of what I want to say is define the context that you're going to invoke that callback from, right? Beware of Hyrum's law, because regardless of what you document, people are going to depend on all of what thread is this happening on? What thread is this not happening on? Are there any locks being held? Hopefully not, but that's not always true. In the case of event listeners, where more than one callback might be triggered for a given event, what order do you call them in? Is it the order they were registered? Is it the opposite of the order they were registered? Is it randomized? In the case of an eventual consistency API, do you happen to call the callback every time you change? Or do you only trigger it periodically, right? Anything that you do here, any choice that you make here is going to be dependent on quickly. This is remarkably fertile ground. Mixing up the behavior between build modes or randomizing it in some fashion might help. But most importantly, be as clear as you can be about when and how the callbacks are going to be called. This is a place where a ridiculous amount of pedantry is actually probably warranted, but we don't usually stress this enough, and we don't stress test these interfaces nearly as much as they deserve before we release them into the wild. If you don't plan ahead, you're going to be supporting whatever you happened to do indefinitely, even if it's inefficient. Polymorphism, I don't have to talk a whole lot about that. Remember, those things are going to be super hard to change. I have about once a month, I encounter in code review someone that is adding a new derivative of some abstract interface class, and some method that they're overriding on that class. It's like, man, that is not how you express that. Like, you're passing just the weirdest set of parameters, and you're missing a const, and that shouldn't be a pointer, and that should, like, all of these things. And I'm like, could you fix this? And they're like, nope, there's 5 of these. We'll plan for it in the next sprint, maybe. I'm like, well, right? They won't, right? We know that they won't, but I'm going to complain at them, and I'm going to make them file a bug and all of those things, right? But my point here being, if you're building a, class hierarchy, spend like 10 times more time on the API design in that hierarchy than you would have otherwise. You'll thank yourself for it. Otherwise, the normal form of extension in C++ is templates and ADL and those sorts of things, right? And this is just, hey, you want to play nice with my type or algorithm or system or interface? Great, let's do it. Again, just document things. Take it slowly and carefully. And interestingly, once again, document the intent, right? We see this example with std_accumulate. A couple years ago, we changed the rules, the specification of std_accumulate from it was pretty much guaranteed to, I think it was straight up guaranteed, to do copy assignment for the accumulator, right? So if you fed a vector of strings into it, it was going to inefficiently copy assign the accumulated string over and over again, right? We debated for a good long while whether it was okay for us to change that to prefer move assignment, right? And in the end, we said yes. I forget if that was a 17 or a C++ 20 change. And most of the reasoning for that was I could tell this isn't actually going to break anything. I did a bunch of research on, like, does anyone actually have a move that is slower than a copy, or where the semantics are different between copy and move? Nobody does, or we don't care enough to manage, right? So it was okay, we made the change. But after the fact, in preparing this talk, I think the more interesting point is the intent of accumulate is accumulate, right? If we actually specify the precise mechanisms and machinery of I'm going to call copy assign, or I'm going to call move assign, right? That is sort of piercing the abstraction. And so I think we made the right decision, but maybe not with all of the right reasons, right? I think matching the intent of what should accumulate do is a better answer. As far as like callback protocols go, we saw great examples with the command line flag parsing for abseil. So in this, if you want your type to be valid as a custom user type for a command line, you need to specify parse flag and unparse flag. And we have constantly encounter, like every 6 months or a year, we encounter some new clever way that people are taking advantage of that relatively simple protocol, right? If you implement your command line processing by calling parse flag on every argument in argv in order, then a clever user can build a stateful flag type that tracks how many times it has been called, and either build repeated flags out of that, or have semantic differences in their code based on whether it was explicitly specified on the command line or is just the default value, right? And I don't like any of these as like, your code is gross, don't do that, right? But as soon as we gave them the extension points like this, without mixing up the protocol to make it impossible to do that, of course, clever users will do that, right? We find gotchas like this hiding in even this very simple protocol every 6 months or so. It is very subtle to get all of these things right without accidentally giving out extra functionality, which you're going to have to support indefinitely. So in conclusion, configure based on outcomes and intent, right? Your configuration is actually abstraction on its own and deserves some design. And that is a novel sort of space for us to be doing design, but I think it's very important. And your customization, whatever you do there, is going to actually fight over time with optimization and maintenance, right? The short-term thing that you do today to satisfy a user by giving them the ability to have a bigger buffer size is going to preclude you from having full control over the system in the future when you need to specify those things yourself. Extensible interfaces are very hard to get right. and very, very hard to change after the fact. And the popcorn button is a trap. Questions?
Hey, Titus, thanks for the talk. So with enough users, it's not possible to know what all their use cases are.
Yep.
And you can't tell users what to do because that's not how Hyrum's law works.
Yep.
Do you think there's a higher level analysis here where users who are setting configuration like 1 or 2 sigma outside the mean should really be using a different API?
Oh, probably. I'd have to think about that. I think one of the problems that we have is so much of this configuration is, like, I can tell when the default is left intact. That's static. But so much of the rest of it is dynamic. And I think we've only recently, again, it's kind of Matt's fault, we've only recently gotten better better ability to get like runtime telemetry on those dynamic configurations to even figure out where those like far outliers would be. But my suspicion is that probably the majority of those far outliers are just bugs. So I think there's a lot that could be very interesting to research on this, but I don't exactly know what the next step is. I suspect that, yeah, you're just holding it wrong or you're looking for a different tool is one of the possible outcomes for sure. So, Matt.
I see a lot of complex configuration things for things that are essentially caches or memoizations. And I was wondering if you had thoughts for what a good interface for the configuration of such a thing is, because everything I've seen is bad.
I've only seen the things you've seen. They're all bad. Like I believe that if we sat down for like 6 months, we could figure out how to properly design one of those in the modern era. But yeah, I've only seen bad designs. So, Daisy.
So you talked a lot about interfaces that provide information that's maybe external to the semantics of the algorithm, that's maybe not part of something you should rely on in a test. Is this something like what we had in, say, executor properties in P0443, where we had external to the semantics syntax? And should we have a separate syntax for this to make it clear that this is something you don't rely on in a test?
That was a deep one. I can't do that on the fly. Let's have a glass of wine later, and we'll dig into that deeper. But yeah, David.
Hey, so there's a lot of benefits to having generic interfaces in terms of they get more use cases potential out of them, and then there's benefits of having more narrow interfaces, which means that you can maintain it more easily. So what criteria would you use when you're designing software to decide whether or not you want to go with a generic interface or a more targeted narrow interface?
I'm a computer-hating Luddite, so I would go with do the simplest thing for as long as possible until you have no other options. And then you can make it generic, and then 3 years later you're going to hate yourself. Like the old Google command line flags API many years ago, and which we released as G flags, I think, just kind of threw it over the wall, open source. Only worked on 7 types or something like that. Like, it was modestly annoying in some cases because it was a little restrictive. Like, there are other things that you might want to specify, like lists, for instance. Durations, like having type-safe timeouts actually seems like a pretty good one, right? And so we came up with this like long list of reasons why it was valuable to make that totally generic. We're going to make it like, here are the ones that work out of the box and you can plug your own things in. And it was like 3 weeks later that we're like, wait, people are doing what? Like they had values that didn't like round trip, and like if you call, parse and unparse on it, it didn't come back, and like all sorts of things, because just defining that protocol accurately and carving out enough room to like move it forward, to say nothing of having good taste, like these things are just super, super hard. And so like, in my mind, like, keep those things very, very closed if you can. I don't actually regret it, but it was more complexity and more cost than I realized when I started. So.
For the cases where you do find those huge outliers, the 256 byte example and things like that, what do you do when you find them? Do you just run away screaming, or do you find cases where, no, we really need to go investigate this because this interface is so bad, we need to help the majority case people who are accepting the defaults?
I'm pretty solidly in the camp of I'm going to optimize for the whole fleet, not for those special cases. And that will sometimes mean that your special case regresses to some extent. One of the things that I think is really critical, I think it might have been a Lawrence Lessig quote from like 20 years ago. Nowhere in our system of laws are you given the right to assume that you continue doing business in the same fashion, right? And similarly, when you're providing an API, right, I'm not going to promise that you can always like micro-optimize without having to react to any changes that I'm doing, right? Especially if I can prove that like, this is going to be worth 1% of fleet performance, but your thing is going to get a little slower. Like, okay, sorry, not my problem. Like, I'm going to do the thing that's the greater good. But that is hard because taking no action is very easy to do. And all of the users that are missing that 1% boost don't know it because you're not, trumpeting it from the rooftops. Whereas the one user that might actually notice that hyper-tuned, interface usage, they will actually notice, right? And so like, it gets into this sort of social negotiation thing, and maintainers of critical libraries, or certainly low-level libraries, have to balance that trade-off of, do I give you these knobs? Do I support your existing weird usage? Or do I optimize for the broader thing? And that requires saying no to a lot of things. And we don't like saying no. I'm starting to like saying no, but so I think it's over here.
A major class of configuration that I've seen specify exploitable properties of inputs and exploitable semantics that can't necessarily be assumed in the general case, but that can be very much a moving target with infinite growth for expansion, but doesn't fit within the outcome model, yet it doesn't seem like we should leave that on the floor. So where do we go from there?
Do you want to give me an example?
I know that my floats have no nans in them.
Right. Wow. Oh, you said the scary one. Yes.
You're wrong.
Matt says, you think you know that your floats have no nans in them. You're wrong. But at the same time, like, all of your reasoning about how do you do floating point math pretty much predicated on the idea that your floats have no nans in them. And I think that this is one of those, like, the emperor has no clothes points, where a talk that I gave a few years ago was about non-local properties of your types, right? And string view and double is one of the examples, right? You can use string view safely if you know certain properties about your program, right? You know that that buffer is going to live and isn't being mutated. You can use double with great safety if you know somehow that you have no nans, right? But you have to kind of define that on the tin, or you have to spend a bunch of effort doing the other thing. And I'm not sure if that's configuration so much as that's like, we need to be clearer about what invariants, like what structural invariants we're relying on for the safe use of those interfaces. Does that answer the question?
Sure.
Sure, okay. We got time for one more.
Do you have any suggestions for deprecating knobs, or besides The one you gave where you make the default explicit.
So one of the things that we've found works pretty well, especially when they're like optimization and performance tuning knobs, just start ignoring them. Like, you're not changing the semantics. Just make it a no-op and see if anyone complains. And you go like a few months, and when no one complains, then you go through and you delete all of their usage of it, and then you call it good. So, thank you very much. We're out of time.